All right, so make sure everyone sees the correction there. We were trying to find the slope of the tangent line x equals 2, so I was plugging 2 into the function itself, right? And my synthetic division, 2 times 0 is 0, not 2. Sorry, going too fast. So when we get over here, it should have been -1, not +1. Thank you for pointing that out. Are we good though with this next step as well then? Plugging in 2 plus h? Everyone feel okay with that? So understand here, this is us just setting it up to go find the average rate of change. The limit will convert that from an average to an instantaneous force. What happens is those 2 points get closer together so much so that when we subtract the two x values, even though it's not 0, the limit allows us to treat it in a way that we're saying it's so small that we would interpret it as 0 at some point, okay? With that in place, so I'm going to work this out a little bit quicker than we have because we've seen it, but I want to make sure to spend more time on the difference quotient here in a second with another problem. Okay, so I squared the first one by, you can write it twice and FOIL it. I distributed the -2 in the next one. The nice thing about this, when we go over here, those drop to 0, okay? With that in place, we'll have h squared plus 2h minus 1. Now, we like to see the -1 here because what did we just correct my first step to be equal to? -1, right? Does everyone see that? Those being the same, when I go to subtract them, they're going to go to 0. So that's definitely an encouragement to see that, hey, this matches what I found up here. Okay. With that, we can now go to our limit as h approaches 0. Just make sure you see we're going to do h squared plus 2h minus 1 minus -1 all over h. But as mentioned, these go to 0. A number minus itself is always going to be 0, okay? And what do we like that both the first two terms have on them? Right, since these both have h's, we can simplify it a little bit further, right? That'll go to just h plus 2. And we really like this statement because the denominator is no longer h. So what can I do with the 0 to evaluate my limit? Or I could do, does everyone agree with that? Direct substitution here? Remember, we couldn't do direct substitution from the beginning because that would make my denominator 0, and we'd either be in an indeterminate form or an undefined form. So we couldn't do much. But now that we've been able to simplify, we're in a situation where, hey, now I can evaluate this. Okay. So with that in place, we would say, hey, this equals 2 by direct substitution. But also remember what we were actually trying to find was the slope of the tangent line. Okay. Now, for the sake of space, I'm going to copy this out of here. That was just make sure you see, I'm just taking away that because we used it to set up our average rate of change, right? We simplified our average rate of change, and then the limit can now be evaluated through direct substitution. That's where the 2's coming from. Now, does that 2 feel like it's random to you? When you look at this function we started with, is the 2 random, or is there a 2 somewhere up here we might be able to connect it back to? Are there any 2's in this one I have highlighted? There's a x squared and a minus 2x. Now, we probably shouldn't connect it to minus 2x, though, because this is positive 2, right? If we go back to the lines we were looking at last time, when we go back to this one, remember I did this one a little bit more quickly, just focusing on the simplifying the difference quotient, right? What you saw here though is the signs matched. Okay. So one of the things we're going to look at today is kind of start connecting different types of functions to the results we can expect. The good news is hey, yeah, we're having to do the limit definition of something right now. But once we establish it, do we have to keep doing this over and over and over again? Not necessarily, right? There's going to be patterns we could follow. Like getting the slope of a line, we don't have to do this each time because we know the average rate of change and the instantaneous rate of change are going to be the same when we look at a line. Okay. This one's a quadratic though, right? It's a parabola. And what we just found is that, hey, when x is equal to, the slope of the tangent line is 2. Okay. What do we have to do then to find the equation of a tangent line? All right. So remember, if you have a point and a slope, you can use the point slope form. This is definitely something you're going to want to use. I know it's not the only way to deal with this, but it's the most direct way to deal to get to what we want. Remember, we had a point because we went plugged in 2 earlier. So don't forget that we have the point we needed because that's the specific location of our graph we're focused on. With that said, we just found the slope of the tangent line. So we could go then plug these values in, y minus -1 equal to 2 times x minus 2. And then solving for y, this right here would be the equation of the tangent line. Any questions where I'm getting that equation from? Now, the next thing, this step is go look at the graphs, right, to make sure we see how this is even a part of that. So that's what we're going to go look at next. But is everyone good with where the 2x minus 5 is coming from? All right. So make sure you see what we're saying is this function, right? When we're focused on when x is equal to 2, this equation will give us a line that is tangent to the graph. Okay. The slope of that is the instantaneous rate of change at that point, but this line is tangent to the graph. So that's where we're going to go to next and make sure to graph it and visually see that it is indeed true. So with that, I'm going to go ahead and copy these 2 things that we have. We're going to go over here and look at the graphs. And it did not copy properly. Was it -3, -5? Now, there's different ways to handle graphing the quadratic. I'm going to graph the quadratic first, though, because that is the focus of what we're dealing with. Things to remember as far as the vertex of a quadratic, that is the minimum or maximum value of it. If you have it in the standard form, remember it's h equals negative b over 2a, and then just plug that in and you'll get your k value. So as far as getting that vertex here, thankfully, it should work out rather nicely. It's not going to be perfect, but h will equal -2 all over 2 times 1. So it ends up being just 1. All right, if we plug 1 into that equation, so f of 1 we'll get -2. If I remember right, didn't we just say f of 2 equals -1? So we have that point still as well. But the whole idea is here, this is our vertex. All right, as far as graphing quadratics, remember, this is definitely the piece that we want to focus on to say, hey, at f of 1, -2, this is going to be what sets up the rest of my graph for the quadratic, okay? With that said, I can plot this point, but I also know I can plot this point now without plugging anything in because of the axis of symmetry. With quadratics, remember that an axis of symmetry exists right through the vertex where the left and right are going to have the same pattern of behavior. Other points I'm going to put to help myself will be these. Okay. The idea is if you go in your function, you plug in -1 or you plug in 3, you should get those values back. 0 equals -1, you could have looked at the function and grabbed the constant term. Make sure you see that as well. But this will be the graph of my quadratic function. This is f of x. Any concerns with getting to that graph from a standard or from the general form? All right, so just make sure you see here then, just to close it out, I came over here to get the vertex first so that I knew where this was. For our particular problem, that was the minimum point of our graph, okay? Everything's gonna go up from there. That's the nice thing about it. This little point we just did the work for, right? That was the whole focus of it. Whenever we go forward with this point is the focus of everything we're doing right now, okay? With that said, the next thing to go graph then is our tangent line. So let's go do that. The good news is you could focus on that saying, hey, go through -5, then up 2 over 1. And when I draw that line, how many times should it intersect my graph? 1 time. All right, so if I zoom in here, what we should see is that it's only, well, my zoom's not working, sorry, y'all. When we zoom in here, what you'll see is that, hey, I'm drawing it by hand, of course, so it's not gonna be perfect, but it's only gonna be touching the graph at that point. So that's why we call it a tangent line. The interesting part here is if you zoom in enough, will you be able to tell the difference between the curve itself and the tangent line? And another way to say this is we can kind of locally linearize an equation to help something be a little bit easier to work with, right? That's why I made sure to point out over here with that one that we did yesterday. Sometimes an average rate of change is good, but this definitely doesn't help me with that piece of the graph if we're trying to explain that behavior. There's a big difference between that and the average rate of change. So sometimes it's just simple like, hey, let me get that average a little bit closer to help me with that. Well, that's the awesome part about the limit, right? It's allowing me to get it so close that we can actually look at a single point now. Okay. So yes, Wednesday, we definitely talked about instantaneous rate of change. As we move forward with this, different things that I can ask for is find the slope of a tangent line. Identify the instantaneous rate of change. Okay. Those are definitely terms that you want to be comfortable with. But as I also mentioned at the beginning of this, we're going to want to expand from this, not at just a single point, but what about over an entire function? Can we do this looking at every point of a function? Well, as long as a function is continuous, we definitely can do that. Okay. There are some exceptions, and as time permits today, we'll look at those exceptions. Okay. But are there any questions with this before we go to another perspective of this? I know I have the graph here, but we're okay with the work and everything too? Mhm. Now, keep in mind, the only thing I took away from this is where did I get the f of 2 plus h from, and make sure you plug in 2 to get the -1, okay? This is us just visualizing why would we do that, all right? I now have a very good perspective what's going on at 2, but what if I wanted more than just that 1x value? That's where this next definition becomes very important, okay? So I'm taking this from it might be an older edition of the book, but I'm sure it didn't change much. But what you'll see here is there's a new notation with the function that we're going to be working with moving forward. So if we're working with something that we know is a function, that this function is continuous over the domain we're focused on, we can use this to define what we call the derivative of the function at x. Okay. Now, as you just saw, we focused on a specific x value at x equals 2. We did the same thing. So the only difference here is this is going to open it up for us to call it a derivative now, right? So moving forward, hey, let's find the derivative at x equals 2. Well, that's the slope of the tangent line. That's the instantaneous rate of change. So instead of saying all those other things, I'm now going to say find the derivative. When I say the derivative, though, make sure again, things like slope of a tangent line, instantaneous rate of change, all that needs to start coming together for you. Okay. With that said, make sure you see the directions. And my problem that I have to go with this, say differentiate the following function using the limit definition of the derivative. Okay. Differentiating it is taking a function and getting to a new function that we're going to use this new notation for. So make sure you see here that we're going to have a new notation for it. Okay. But that new notation is going to be f prime of x. Okay. That's what we're going to call it. But that's going to mean that, hey, this new function will help me find the derivative at any value of x as long as the function is continuous on the interval we're looking at. So for this first function, I gave us 2x minus 3. Okay. So as you're writing the directions for this one down, make sure you're noting to yourself, this is definitely the function that will give us a line. So it's continuous for all real numbers. So when I go forward with this, I can do it for any real number I want. Now make sure you see here, if I'm telling you to use the limit definition, this is very important. That's what I expect to see. And I've done several different equations now, just as far as this isn't going to be the whole first test, but I would say expect at least one problem next week's test, right? That focus on the limit definition, right? If I have time today, which I don't know if I will, but more like on Monday, we'll talk about some of the patterns that, hey, we don't have to go through this every time, right? We'll be able to start identifying some of the derivatives of functions and make it a little bit easier for us, okay? Limit properties will definitely make it easier for us, okay? So that's some of the stuff that we'll look at on Monday more than likely. But as we go through this, make sure you see right away, we're going to say, hey, what I'm trying to find now is the derivative of my function. So f prime of x equals the limit of f of x plus h minus f of x all over h as h approaches 0. Forgot that part, sorry. So again, we have f of x this time, so we don't need to go look for it. Just make sure you see again, we're going to have to go plug x plus h into our function and simplify that. The good news is just distribute the two and you have what we need, okay? This is more about making sure we're comfortable with the new notation and what I mean by the directions here. But the nice thing about this, hopefully you're already like, oh, I should be seeing a 2 when I'm done, okay? Because as I go through this, then f prime of x, or the differentiated version of our function, equals 2. Okay. Now, this is where it's a little bit different than before. Even on the previous one we just did, we were focused on x equal to 2, right? So when we were done, we were saying, hey, the slope of the tangent line at x equals 2 was this value. We focused on a specific thing. Here, by leaving x in there and not plugging anything in for it, when I go through and simplify, when I'm done, what we have now is the function differentiated at any x value we want it to be done at. Okay. Now, again, as we've talked about with the equation of a line, the slope doesn't change no matter what points we look at. Okay, so make sure you see here, the way that we would interpret this is that, hey, the derivative of my function is 2. Well, it doesn't matter what I plug in, then if I say go find f prime of 0, well, the answer is 2. We can change 0 to 100. It's 2. F prime of pi, guess what? It's 2. We don't have to go through and do the limit definition for any x value that we want to work with now. We've helped consolidate it because we know lines are continuous for all real numbers. Hey, I did this one time for any x value I need. Hopefully, again, as you kind of just copy this down, if you need to fill in the gaps, make sure you fill in the gaps. I definitely skipped steps here. The two things I wanted you to take from this is that, hey, I put the new notation in for a derivative function. F prime of x, that's how we use function notation to identify, hey, this is a derivative. It's not the original function, but it is the derivative of the original function. It's also the directions that I've stated here, okay? If I want you to differentiate this going through and using the limit, I will tell you to do that. Okay. Here on the previous problem, when we're looking at that quadratic, we went through this process to get to something, right? So this is, hey, we wanted to go through it to make sure we're comfortable with everything. That's why I said if you need it, I wrote out the work, right? But as we go through this, the big difference was we were doing this for a specific x value, so that's why we took this path. Well, the good news is, what if I changed the x value and said, oh, okay, how about x equals -3 now, right? Well, instead of having to go do this whole thing again with -3, we can say, hey, I did it once and for any x value you want, and all I have to do is go plug in -3. I just have to make sure to use the derivative function so that I can get that slope that we're looking for. Any questions with that? Okay. I was just saying, if you plug in pi, I picked something random that it was just like, hey, if I try to say what's f prime of pi, well, f prime equals 2, so it equals 2. I don't care. I could have just thrown anything in. Okay. Now that wouldn't be fine. This part would not be fun, right? If I try to find f of pi, right? Because we'd have to plug that into the first one, which is not too bad. It'd just be 2 pi minus 3. And if you need the decimal, plug in your calculator. But if it equals 2, I just want to exaggerate that. Hey, it's just 2. Okay.
Sounds like that popped out of nowhere.
Yeah, it was just me trying to exaggerate that the slope is always 2, right? So with that said, though, as mentioned, we have to be careful, all right? Not everything is differentiable. There are some restrictions. So as one of the things I point out is make sure we understand the function has to be continuous. So this is a great example that I felt from the book gave a good visualization of this. So when we look at this graph, what are some letters there that highlight an x value that is not continuous?
F.
E, F,
B, right? And make sure you see we're focusing on all of these situations, right? Those are 3 situations that we look for as far as being discontinuous, right? You have removable, you have a jump discontinuity. Make sure you see here, the only one they didn't put would be an asymptote, right? If you have a vertical asymptote, we've already looked at that. We can't use it anyway. So that would be an example of it's not continuous as well. What you're going to find is, though, there's another one that we can talk about. But if I kind of zoom in here, what graph does that begin to look like where it's more of a V shape? Anybody remember the V shape graph? Absolute value, okay? What you'll see is you have to be careful about the behavior of a term, right? So with polynomials and stuff, we get nice kind of smooth turns. So if we look at our graph here, where did my graph go? There it is. That's a nice smooth. Now I didn't draw it very well, but we were expecting that to be a nice smooth turn, right? What you'll run into is our book calls it a corner. Another name is a cusp. If it's ever a sharp turn, then what you're going to find is that you can't differentiate it. All right. This is a tough one because it is continuous. Does everyone see that? If we look at plugging it in, I can definitely plug in the point, right? The limit will point there, the limit will point there, but this is a situation where we would say, hey, it's not differentiable. Okay, the reason that is, if you think about it, I could do this line in its tangent, but now all of a sudden I can do this line in its tangent. It's not clearly defined at that value when we start trying to do the derivative of it. Okay, is that clear to everyone? We could dig into more. Well, guess what? That would be another example of a corner or more of a cusp taking place. Okay, what you'll see there is piecewise functions often can create this. An absolute value can be written as a piecewise function. Those are things to watch for. Okay, so know that when you're dealing with that, those two values would also be situations that we would say, hey, this is not differentiable. Because there's a corner, or also no, I'll call it a cusp, but the book calls it a corner, just so you know. All right, well, at that point, make sure you see here, this point's fine, this value's fine, these values are fine. That brings us to this last one. What is special about this one when you look at that? They kind of drew the tangent line there for you. So when you look at this one, what do they do with that tangent line? It goes vertical. If there's a vertical tangent, it's not differential.
Is
That would be
same as like with,
No. So this would be a situation if you think about like the cube root of X. So if you have the cube root of X, you'll have a graph that does one of these that quite possibly have a vertical asymptote there. All right, the problem, not asymptote, sorry, vertical tangent. The problem is that puts a zero in the denominator. Because remember, at that point, the slope of this tangent line here is gonna look like some value over zero, so it's undefined. So there's ways to kind of suspect it is happening, right? But that's where then we'd go into the work to say, hey, do I have a vertical asymptote or is it something else? Oh, hey, it's a vertical tangent might be, okay? Like if you know you can evaluate the point, then there might be a tangent, okay? But what you'll find is we will say is I can't differentiate it. So as I just did this work here, I chose a line first because we didn't have to worry about that. Moving forward, there are some things that we have to watch for, okay? So the graph has to be continuous. The function, I mean, has to be continuous and it has to have no corners or cusp in it. Right? Then I can differentiate it. With that said, just know that as far as dealing with functions, as we'll do in our class, oftentimes you can limit the domain to fit what you need, right? If you have a function that, hey, over the domain I'm focused on is continuous, then we're not worried about any restrictions or issues outside of that, okay? So keep that in mind. So like for this here, we could say, hey, my whole focus was just this piece of that entire function. Well, then all these other issues don't matter because I wasn't focused on those. We can work around it, okay? Any questions with that? I don't remember what page I got off of. Let's see. That was page 140 in the old textbook, so I would expect it to still be 1, 2, 1, 3. All right, so here's another one. I think this will be a good place to kind of close out our discussion, because as you write this down, what did I change about this problem? Other than the function itself, what did I change?
It's not fun.
Yeah, so it's a normal function, right? It's not a differentiated function. Doesn't represent a derivative, but I want us to find the derivative, right? Can I find a derivative of a derivative, by the way? Yeah, as long as it's a function and it's continuous and everything, you keep taking derivatives now, right? That would be one thing we look at. But it would be important to check what we're starting with, right? It's always important that, hey, this isn't necessarily derivative unless the direction stated differently, of course, okay? What do my directions say though? Differentiate, right? Did I say use the limit definition? Not necessarily, right? So if I didn't say it, what is the derivative of this? -5. How do we know that? right? That's a line, right? MX plus B. And as we've shown multiple times now, that if I went through that whole process, I'm just gonna get that value. Yep, if you don't believe me, then just go work it out. Go say, hey, G prime of X equals G of X plus H minus G of X all over H. Okay. We'll say G prime of X, nope, what did I forget, of course? What's the most important part that allows us to do this? The limit, right? And again, I'm going through this quickly because we've done enough lines like this. I'm just making sure to connect it all together. Okay.
Is there a point where the end value is not the same as the derivative?
What do you mean?
Like, like it would be -5, right? Because and the slope is -5.
Yeah.
So that is not to each other.
So vertical lines, remember, would be one issue. So when I say lines, they have to be horizontal or increasing or decreasing. Vertical would be one example, okay? This would be the other example I'd point to. If I'm not working with a line, then guess what? If I go look at other tangent points, this one's gonna look different than this one, right? So it's gonna change as we go through our function. What you would expect to see here though is when I do my derivative, there probably is gonna be an X left over.
And the reason why that's not considered a line is just because.
There's a curve to it, is the main thing.
Okay.
When we think more of a line, it doesn't twist, turn at any point. It follows that same rate of change the entire time. Whereas here, what we'll begin to see is that, hey, this has a different behavior because as I go from one point to the next point, that rate of change is no longer the same. Right? Now, some rates of change can equal what though? So what would the slope be? Right, so make sure you see here as we deal with this, that's something that we can definitely run into is a slope of 0 for our rate of change, okay? Does that kind of help with that question? So here, hopefully what you'll see is if I tell you to do the work, then we need to do the work, right? Everyone follow me with that? Testing the what, next Friday, I said, right? With that said, though, if I just say differentiate it, then we're gonna start working to a place that we could say, hey, as far as the directions, I need to do what I'm comfortable with. If I can look at this and say, hey, that's a line, the rate of change is always gonna be the slope, bam, that's my derivative function. Just make sure, again, you see here, what did I put with my notation? Prime of X, right? Now, what we're gonna see though is what, on Monday, as I mentioned, we're not gonna have time today, we're gonna look at some other functions that we can begin to follow patterns on. That, hey, I don't have to go through the limit definition every time. This is important, right? It helps set the foundation for everything we're gonna do moving forward with derivatives. We needed this in place. We need to understand how limits work because it definitely is good for explaining the behavior of functions. Limits allow us then to get to instantaneous rate of change. That's where the derivative comes in, all right? That's why we need the derivative. We're able to go from what we'll see as we move forward, delta X, oh, sorry, not delta X, the change in Y over the change in X to we're going to introduce a new notation of dy dx. But that has everything to do with limits. So that's why we started the course with talking about limits because it helps us mathematically move forward, okay? So know that moving forward, our next steps is not to just look at lines, but how can I get to the derivative of a function based on patterns and different rules that we'll have in place, okay? Any questions as we finish up today? All right, well, if you don't have any questions and have a good weekend and know Monday, we'll kind of start My goal is to just kind of make sure we practice this Monday and introduce those few patterns. As far as the test is concerned, make sure you understand it's gonna be probably a little bit more limit heavy. I'm gonna do my best to have a practice test out for y'all by Wednesday, okay? So you kind of see what to expect.
Is
Yep.
it-
It's gonna be a paper test.